What is conditional distribution? We have seen this in the past. Conditional probability distribution. When I said only distribution means I mean probability is implicit. So we know what is conditional, right? Measures the probability of an event occurring given that some other event has already occurred. Okay, this is what it is. That measures the probability of occurrence of an event given that another event has already occurred. This is coming from the past. You know this. Some event has already occurred, and what does it give? That some more new information has come, and on the basis of new information, we should update the prior likelihood that we have, and then we get the posterior. So this provides a way to update our belief of likelihood, okay, based on new information. Okay, based on new information. So what is the old formula that we know already? Probability of A given B is equal to probability of A and B by probability of B only. So do we know these things already? What is this? This is our conditional probability. Okay. What is A and B? Combined probability. These are joint probability. And what is the probability of a single random variable? This is my marginal. So we have seen this joint and marginal already. This is conditional. So combined one is joint, individual is marginal, and A given B is conditional. So what this gives me a beautiful formula, that conditional probability is implicit in all is equal to joint by marginal. Okay, this is the relation. This ties up all the things, three things together. And let's understand the joint one with the same example again. Conditional probability. So I'll formulate this. So the running example, the ball example that we had. The extra information. So now we have that. So now I'll write the question. So this is the setup, we know that already. This is our setup, we have seen this already. So let me formulate a new question, a conditional probability question. So my question here is, what is the probability of drawing a red ball in first draw given that a blue ball is drawn in the second draw. So what was the random experiment here? What was the experiment? That a ball is randomly drawn from each bag such that both the draws are independent of each other. So there are two bags, A and B. Each one had 2 and 3 red and blue balls. Okay. And then what we have done, let A and B be discrete random variable associated with the outcome of the draw from first and second bags respectively. And now my question is, what is the probability? This is the conditional probability question. That what is the probability of drawing a red ball in the first draw given that a blue ball is drawn in the second draw? Let's solve this. So same example, just some manipulations here. So what was this? What was the, let's redefine this. So A is the drawing first draw from the first bag. Okay, first bag, first draw, red ball. And what is B? B is for the second draw, and this is blue ball. So let's write it down as conditional probability. Probability of A given B is equal to, we know that blue ball has already been drawn. What is the probability of red ball? A given B is probability of A and B by probability of B. So let's find it out. Okay, what is the probability of A and B? What is A and B? So what is the probability of drawing a red ball, the joint probability, in the first draw and a blue ball in the second draw? This cell will give me this cell here. This is 4 by 25. So this is my joint distribution, joint probability. This is equal to 4 by 25. That is a red ball in the first draw and a blue ball in the second draw. This cell will give me here. So this is the value 4 by 25. And now what is the second one? Probability of B. That is probability of drawing a blue ball in the second draw. So this is our probability of B cell. Probability of drawing probability of drawing a blue ball in the second draw. So here it is. So these are the values here. Let me highlight them. So probability of drawing a blue ball in the second draw is given here. This is for the red ball. This is for the blue ball. So this is 2 by 5. 2 by 5. 2 by 5. So 5 times 2 times. So this will become 2 by 5. So the probability of drawing a red ball in first draw, given that a blue ball is drawn in the second draw, will be given from the, so let's see, just match it. It's a simple toy example, so let's match it. Probability of drawing a red ball in the first draw, that is from the first bag, given that a blue ball is drawn in the second draw. So this blue ball is drawn in the second draw, so this is gone. Okay, so this second draw is given. So what is the probability of drawing a red ball from the first draw? This is 2 by 5, and that's what we got. I hope conditional probability is clear. And remember that we have only got these values. This we are rechecking. This information was not present. We didn't have this information. We only had these joint probabilities and these individual probabilities. From this we calculated that this is 2 by 5, and we found out that yes, this is 2 by 5. This information was not available with us. Okay, this we calculated from this, all these joint probability. We started with this, right? These values, and then we got this. Okay, I hope conditional is clear. So let's formally define conditional CDF quickly. What will be the conditional CDF formula? So this is, so now mark the notation capital F, X given Y. X, earlier it was comma, this is that straight line. X given Y is equal to probability of X less than or equal to X given Y is equal to Y. So here it is Y is fixed, and now probability of all the values of X less than or equal to X. So this is the accumulation is happening on the X variable only, and Y is fixed. And this is Y has happened. Now what is the probability of getting all the possible values of X less than or equal to X? So this is what conditional CDF will give you. Okay, so discrete case. So I understand this is repetitive, but this will give you a very strong repetition, will give you all the formulas feel. Okay, what formulae? Okay, what is the discrete case? Fx again given Y, single line is xy. The notations, be very careful when is comma is and this is given. Okay, these notations you will keep on finding everywhere. So this is probability of X less than or equal to X given Y is equal to Y. Y is fixed. This is equal to summation xi less than or equal to X, only one summation, X is equal to xi given Y is equal to Y. So this is Y. So all the possible values of X given Y is fixed at Y. That has happened. The universe has changed, and this is my limited set now. Similarly for continuous case, so we have new information, and in the light of the new information we have to update our new probability. Okay, so this will give me minus infinity to X. Same thing, f of, this is my PDF, X given y, this is x comma y, and this integrated over dx. Okay, is equal to, I'll expand it a bit, minus infinity to x, f of x given y. Okay, no, so let's expand it and put the conditional value. So I'm expanding it now, right? So f of x comma y by f of y dx. So remember this comma, this is and this is given. Okay, let me correct this notation also. This will be x given y. Okay, and then always remember, whenever the conditional probability is there, right? So there is one for mathematical this thing, right? So this should not be 0 whenever you're dividing something by 0, right? So this will be across probabilities that such that probability of b is greater than 0. So everywhere you have to put that. Remember this condition, that such that probability of f of y is greater than 0. Okay, I hope the formulae are clear and the symbols. This is given, this is and, wherever you see comma, so be very consistent. Understand, this is comma, this is comma, this is given. Continuous case, this is done. Now conditional PMF. So conditional CDF is done. Now let's move to conditional PMF. So I'll always cover all the cases. Okay, so CDF is common to both. This concept is common to both PMF and CDF for the discrete, and then I'll give you the concrete for conditional. This is for discrete case. The conditional PMF would be probability of x is equal to x at a particular point. Now this is not less than equal to. Here you see this is less than equal to. This is cumulative. Okay, and here this is at a particular point. This is equal to probability of x equal to x comma y equal to y by probability of y is equal to y. So again I'll write it. This is your comma is and this is given. Okay, the symbols notations will change. Okay, given probability of y is equal to y is greater than 0. And then similarly conditional PDF will be, what is the value? F of x given y is equal to f of x comma y by f of y of y. Okay, such that f of y is greater than 0. Okay, so there are a lot of applications. You must be thinking, why am I learning so many formulas? So this will make you comfortable with the notations. First of all, you will see all these symbols everywhere, so that will make you comfortable. Apart from that, there are a lot of applications of conditional conditional probability distributions in machine learning. Later on, when we learn generative models such as GANs or variational autoencoders, so there you will see this conditional distribution in play. For example, GANs learn the conditional distribution of the pixels of an image. Okay, what are the pixels for a given style? So what are the combination of pixels for a given style of the input image? So the condition is, what is the style in the input image? Given that, what is the probability of the pixels? So GANs of these generative models, right? The GAN that learns it. Similarly, variational autoencoders also. So this is why these concepts are very important and fundamental. Okay, I hope that's clear. Now let's move to the next topic within conditional. So conditional, now we'll discuss about conditional expectation. I told you, right? So we'll have conditional expectation also and variance. So we'll just extend it. So what is conditional expectation? So we write the conditional expectation of, we know expectation of x is expectation of x. Conditional expectation is again that something has happened, and then conditional expectation of x given the other random variable y has happened, that given that y has happened, the value for that is y. So what will be the example? For example, we have the conditional expectation of person's weight. So we'll have the conditional expectation of a person's weight given its height. So if you have given height, so for example, if the height of the person is equal to 170 centimeter, then what will be its weight? So this information is available. So this won't be the average weight, right? If I ask you the expectation of the weight, then this you will give me the average weight of all the sample, whatever you have. Okay, but if I have given you the more information that okay, the height of the person is 170 centimeter. So now this is the condition. Your universe has changed, the world has changed. It is limited to 170 centimeter people. So the output for this would be the expected value for what will be the expected value? This will be the average of all the weights of all the people whose height is 170 centimeter. That average will give me the weight for the expected value for the weight of a person whose height is 170 centimeter. Okay, so this is my question. So this will give me conditional probability, will give me the height. I hope this is clear. How do we denote it? So expectation of x given y is equal to y. This is equal to summation of all x over all x. This was earlier x into probability of x comma y. Sorry, not comma. X given y, and this is x given y. The other way to write this would be summation over x of probability of x equal to x given y is equal to y. Okay. This is for all the, so this can be written better as xi. This will be xi. This is more readable. This is for all the values of xi, summation x into. Okay. So this is your discrete case. So I'll write it. So this is for your discrete case. What will be for the continuous case? Similarly, what will be the expected value of x given y is equal to y? This will be equal to minus infinity to infinity, all the possible values, x into f of x given y dx, because we are finding the expected value of x, so we'll integrate it over all the possible values of x. So this will give me the expected value of x conditional expectation given that y has already happened. This is not changing, so anyway this will not integrate, so y is constant here. So this is for x, just to remember. Okay, so this conditional expectation, where will we read? So this we will use when we will be reading expectation maximization algorithm later. So when this is called EM algorithm, so when we are reading an EM expectation maximizing algorithm, that time we will use this concept of conditional expectation. Similarly, let's understand conditional variance. So this is nothing but an extension. Okay, so after the arrival of new information, you update your probability. What is the conditional variance? Conditional variance would be similarly, let me write it. Let me write the formula itself. You know what is variance. I will not go through that. Variation of x given y has already happened. It has the value y equal to y. This is equal to summation over x. Okay, and then let me be very careful. X minus expectation of x given y is equal to y. So the distance of all the points from the mean or the average value, this square, given y has already happened. So how do we read it? So this is your distance, this is your expected value, conditional expected value. So this is your mean, conditional mean, and these are all the points over which I am summing up. So distance from the mean, and this square is the square of the distance from the mean, given y equal to y, that y has already happened. So this is how you read it. So there is one more formula that we derived in the last class. This is equal to expectation, and write it in the form of expectation. Expectation of x square given y is equal to y minus expectation of x given y is equal to y whole square. This is your variance. Okay, this is just for completion. You should know this. Okay, so what is so when will the variance change? So you want to find the conditional variance, right? And you are saying that you want to find the expected value of the variance. So when will the variance change? For example, I'll give you a very common example. So when you are driving a car, right? So the variance of the car's mileage when you are driving it within the city, the variance of that value will be different from the variance of the car's mileage when you are driving it within the city plus on the highway. So there the variance will change. So one is within the city only, and and the other sample is other cases where you are driving within city plus on the highway. So the variance of the range of the mileage will be more in the city plus highway case, right? On the highway the mileage is more. So that's what will give you the variation in variance. And then because of the variation, we try to find out what is the expected value of my variance and the conditional variance. Okay, so this is what is your application of conditional variance. Okay, what is the when the conditions are changing, the variance changes, and depending upon the condition, my variance is changing. And why do we need to study this? So there is one term we will discuss, that is called, whatever I have told you in the example, right? So that there is a term that captures, that is called heteroscedasticity. Okay, this is called heteroscedasticity. So this is the measure of changing variance. So when we will learn about linear regression, there I will measure this is the assumption. Okay, this is one of the assumptions. So this is the changing variance. So a model. Okay, so why is it important to understand expected value of, or conditional value of, conditional expectation of variance, right? So there this will make sense when we will discuss heteroscedasticity, that is changing variance. So generally the models assume that the variance is constant. Okay, and if when we are modeling this, so if the model that captures captures this heteroscedasticity, right? This is very difficult to pronounce for me. Heteroscedasticity. So that will give me more accurate results because it is changing some more change. Okay, that is capturing some more change in my input data that we have. So model, I'll write it. Let me write it down. Models that account for changing variance, or this word heteroscedasticity, okay, tend to be more accurate. So this is one use case, as I mentioned, right? Why are we studying this? So I mentioned why are we studying everything. So this will be applicable when we will learn linear regression, and this is one of the assumptions of that. Okay, so that's all for this video.